Module 7, Lecture A, Splits and Validation. By the end of this lecture, you will be able to describe the roles of training, validation, and test splits in model development. Propose simple ways to split a small dataset into separate parts, and explain how improper splitting can lead to overly optimistic performance estimates. Why we split data, separating learning and testing. When building predictive models, it is essential to keep the training data separate from the testing data. During training, the model learns and memorizes patterns from the data it sees. If we test it on that same data, we only measure how well it remembers, not how well it handles new situations. This is like a student who practices only specific questions and is tested on those exact questions, which does not show real understanding. By reserving part of the dataset for testing, we can more honestly evaluate how well the model generalizes beyond its training data. To accurately predict future data, it is crucial to separate the data used for learning from the data used for testing. For example, a hospital might train a model on past patient records to learn patterns related to readmissions. If it then tests the model on those same records, the accuracy will look unrealistically high because the model has already seen that data. By instead testing on a separate set of patients from a different time or population, the hospital gets a more honest measure of how well the model will work on new, real-world cases. When building machine learning models, it is important to keep learning and testing separate to avoid biased results. During development, we adjust architectures and settings using only training and validation data. If we repeatedly check performance on the final test set, we risk tuning the model specifically to that data, which breaks its independence. By leaving the test data untouched until the very end, it remains a fair measure of how well the model handles new, unseen data. This practice helps prevent overfitting and gives a realistic evaluation of performance. Preventing data leakage. Splitting data into training, validation, and test sets is essential to avoid data leakage, which occurs when information that would not be available at prediction time influences model training or evaluation. Data leakage can make a model appear more accurate than it really is, as if it had access to future information. For example, using a hospital bill to predict admissions is misleading because the bill is only created after the patient is admitted. Careful separation of data helps prevent these shortcuts and ensures the model's performance reflects how it will behave in real-world use. Data leakage often occurs during pre-processing and feature engineering when you use information from the entire dataset before splitting it into training and test sets. For instance, normalizing with the overall mean and standard deviation, or choosing features based on correlations computed on all data allows test data to influence training. This breaks the independence of the test set and leads to overly optimistic performance estimates. To prevent this, first define your training set, then perform all pre-processing, feature selection, and model fitting only on that training data, and apply the resulting transformations to validation and test sets afterward. To fairly evaluate a model and avoid data leakage, you must keep separate training, validation, and test sets and treat them differently. Any decisions that use target values, such as choosing variables or handling missing data, should be learned only from the training set and then applied unchanged to the validation and test sets. The validation set is used only for tuning model choices, not for redefining pre-processing. The test set should remain completely untouched until the final evaluation, so that performance estimates reflect how the model will behave on truly new data. Python code, preventing data leakage. This script demonstrates a simple way to prevent data leakage in a machine learning workflow. It uses a very small synthetic dataset only as an example. The key idea is that you must split your data into training and test sets before applying any pre-processing steps. By focusing on splitting first, you avoid letting information from the test set influence how the data is prepared. We begin by importing the NumPy and Pandas libraries, which are essential tools for numerical computing and data manipulation in Python. NumPy lets us work efficiently with arrays and perform mathematical operations, while Pandas offers convenient data structures for organizing and analyzing information. These libraries form the foundation for the tasks in this script, including generating synthetic data and managing datasets. We begin by setting a fixed random seed using the random number generator in the numerical library. This makes the sequence of random numbers the same every time we run the code. Having consistent random output is important for reproducibility because it allows us to repeat experiments and get identical results. This, in turn, makes debugging and verifying our work much easier. We begin by creating a small dataset with one input feature and one target value using 20 data points in total. The feature values are generated with a random normal distribution that has a mean of 50 and a standard deviation of 10. This approach produces feature values that vary in a way similar to real-world data, giving us a simple but realistic dataset to work with. We create a target variable that is correlated with the feature by taking the feature, scaling it by 1/2, and then adding random noise. The noise is drawn from a normal distribution with mean 0 and standard deviation 5, and it has the same size as our dataset. This setup mimics a realistic situation where the target depends on the feature, but also includes some randomness. We create a Pandas data frame from two arrays, one holding the feature values and the other holding the target values. This combines the data into a clear table, with each array becoming a column. Organizing the data this way makes it easier to work with, so we can manipulate and analyze the feature and target more efficiently later in the script. We start by looking at the first few rows of the dataset to quickly understand its structure. Using a method that shows the top rows of the data, we can confirm that it includes the expected feature and target columns. This brief inspection gives us an initial sense of the data before any processing. It also helps verify that the dataset was loaded correctly and is ready for further analysis. We set the training dataset size to 14, meaning the first 14 samples will be used for training. The split index is chosen to match this training size, so it clearly marks where training data ends and testing data begins. All samples after this index are reserved for testing. This separation is important because it helps prevent data leakage by ensuring that any pre-processing is done only on the training data. The code first finds the average value of the feature column using all available data, including both training and test sets. It then calculates how much the feature values vary around this average, again using the entire dataset. Because these statistics are computed on the full data, information from the test set is used during pre-processing. This is a form of data leakage and is considered a common mistake in model preparation. In this example, the feature is scaled using the mean and standard deviation computed from the entire dataset. That means the calculations use information from both the training and test data. Doing this can cause data leakage because details from the test set influence the pre-processing step. As a result, the model indirectly gains knowledge about the test data that it should not have during training. We begin by splitting the dataset into training and testing parts using row positions, taking the first portion for training and the remaining rows for testing. This separation is essential to prevent data leakage so that any pre-processing or statistics are based only on the training data. We make copies of both the training and test selections to avoid accidentally changing the original dataset. By keeping the test data completely separate and unseen during pre-processing, we ensure a fair and reliable evaluation of the model. We first compute the mean of the feature column using only the training data, so we can center the values around this average. Then, we calculate the standard deviation of that same column, again, using only the training data, to measure how spread out the values are. These two statistics let us scale the feature properly. By relying only on training data, we avoid using information from the test set and reduce the risk of data leakage. We scale the training data by first subtracting the mean of each training feature so the values are centered around 0. Then dividing by the standard deviation so each feature has a standard deviation of 1. These steps standardize the data, making the features comparable in scale. Importantly, the mean and standard deviation are computed only from the training data, not the test data. This prevents information from the test set from influencing the scaling process and helps avoid data leakage. We apply the same scaling process to the test data, but we do it using only information from the training set. For each feature in the test data, we subtract the mean that was computed from the training data, and then divide by the training data's standard deviation. This keeps the test data on the same scale as the training data, while avoiding any use of test information during training. In this way, we prevent data leakage and maintain a fair evaluation of the model. We display a message to indicate that we are about to show the mean of the leaky scaled feature, which was computed using the entire dataset. Then, we calculate the mean of this feature column and round it to 4 decimal places for clarity. This example is used to emphasize the problem of data leakage, where information from the test data influences pre-processing steps and can lead to misleading results. We first announce that we are about to show the mean of the safely scaled feature in the training data. Then we compute the average value of this scaled feature using only the training set. We round this mean to 4 decimal places to make it clear and precise. Finally, we report this rounded mean and emphasize that it is based solely on the training data to avoid data leakage. We print a short message to indicate that we are about to display the mean of the safely scaled feature in the test data, emphasizing the correct pre-processing method. Then we compute this mean using scaling parameters derived only from the training data, which prevents data leakage. We round the result to 4 decimal places for clarity and print it. This confirms that the test data has been scaled properly using information solely from the training set. The final print statement highlights the problem of data leakage. It explains that scaling the features using the entire dataset accidentally used information from the test set during pre-processing. This is an issue because it can make the model's performance look better than it really is, since the model has indirectly seen the test data before evaluation. The message serves as a reminder that training and test data must be separated before any pre-processing to ensure a fair and reliable assessment of model performance. This script shows why preventing data leakage during pre-processing is crucial. It builds a small synthetic dataset where the target depends on a feature with some noise, then splits the data into training and test sets. First, it incorrectly scales the feature using the entire dataset, which leaks information from the test set into the training process. Next, it correctly scales the data by computing the mean and standard deviation only on the training set and applying those values to both training and test features. Comparing the resulting means demonstrates that the first approach improperly used test data, while the second avoids leakage and leads to more reliable model evaluation. Fair model assessment. Fair model assessment means checking how well a model will perform in the real world, not just how well it fits the data it was trained on. To do this, we split data into training, validation, and test sets. The model learns from the training set, is tuned using the validation set, and is finally evaluated on a separate test set. The test set stands in for future, unseen cases and lets us estimate how reliable the model will be, such as when predicting hospital readmissions for new patients. This process helps determine whether the model is ready for practical use. If you do not split your data into training, validation, and test sets, you can easily overestimate how well your model works. Training and evaluating on the same data encourages the model to memorize patterns and noise that will not generalize to new cases. Keeping a separate test set that is never used during training is like giving the model a final exam on material it has not seen. For instance, in credit scoring, you might train and validate on historical data, but you only trust the model if it also performs well on a newer, untouched dataset. Strong performance on this fresh test data suggests the model is not just overfitting or getting lucky. When comparing models, especially for high-stakes uses like medical tools or hiring systems, it is essential to evaluate them fairly. If models are tested on different data, or if a model has already seen its test data during development, the comparison can be misleading. To avoid this, all models should be evaluated on the same isolated test set that was never used for training or tuning. Strictly separating training, validation, and test data helps ensure that performance differences reflect real modeling skill and are more likely to hold up in real-world use. Basic data splits. Simple holdout split. A simple holdout split is a basic way to divide labeled data for building and testing a model. You separate the data into a training set used to fit the model and a holdout set used only to evaluate its performance. The model must not see the holdout data during training so that its results on this set reflect how it will handle new, unseen cases. This helps prevent overly optimistic performance estimates that come from testing the model on data it has already memorized. With a small dataset, using a simple holdout split requires care because every example used for testing reduces the data available for training. A common approach is to shuffle the data and reserve a portion, such as 1/4, as a holdout set while using the rest for training. For example, with 400 labeled customer reviews, you might train on 300 and keep 100 aside for testing. After training, you evaluate the model on this holdout set to see how well it performs on unseen data, which is more informative than testing on the training data itself. This provides a straightforward way to estimate model effectiveness, even when data is limited. The holdout split is a simple, fast way to begin evaluating a new model by dividing data into separate training and evaluation sets. It is easy to explain and implement and can quickly show how well a model might perform in practical tasks like predicting failures or sales. However, its results can change depending on which data subset is used, so it should be treated as an initial, approximate assessment. As a project grows, this basic approach is usually refined with more advanced validation methods. Python code, simple holdout split. This script shows a basic example of a holdout split, where we divide data into separate training and evaluation sets. It uses a very small synthetic dataset, so the process is easy to see. The main goal is to highlight how to keep a distinct holdout set for unbiased evaluation after training. By clearly separating these sets, we can better assess how well a model is likely to perform on new, unseen data. We begin by importing the random library so we can add randomness to our program. For example, to shuffle data and create unbiased training and evaluation sets. We also import the math library, which gives us useful mathematical tools. In this script, we use it to compute the size of a holdout set by taking the whole number part of a multiplication result, which prevents the holdout set from becoming larger than intended. We set the random seed to a fixed value, such as 42, so that any random operations, like shuffling data, give the same outcome every time we run the script. This makes the way we split the data consistent and repeatable. Reproducible results are important because they make debugging easier and allow us to compare different runs fairly. We create a simple synthetic dataset as a list of labeled examples. Using a loop over the numbers from 1 to 20, we decide the label for each number based on whether it is even or odd. Even numbers receive the label positive, and odd numbers receive the label negative. For each number, we build a dictionary that includes an identifier, a text field that says review followed by the number, and the assigned label. Then we add this dictionary to the list to form our dataset. The code first checks whether the dataset is large enough to split in a meaningful way by requiring at least 4 examples. If there are fewer than 4, it raises a value error to signal that the dataset is too small for a proper holdout split. This safeguard helps ensure that both the training set and the holdout set contain enough examples to make evaluation results useful. We choose a holdout fraction to set aside part of the dataset for evaluation, and here it is set to 25%. This means 1/4 of the data is not used for training the model. Instead, this holdout set is reserved to test how well the model performs on data it has not seen before. Using a holdout set helps us get a more realistic measure of the model's true performance. To choose the size of the holdout set, we start by multiplying the total number of examples by the desired holdout fraction to get the target number of evaluation examples. We then round this value down to the nearest whole number, so we do not exceed the intended proportion of the data. Finally, we ensure that this number is at least 1, so the holdout set is never empty, even for very small datasets. To avoid changing the original order of a dataset, we first make a separate copy of the list of examples. We then shuffle only this copy using a random shuffle function, so the original sequence stays intact. Randomly reordering the copied data is important because it removes any built-in ordering patterns. This helps create training and holdout sets that are more unbiased and not influenced by how the data was originally arranged. We start by splitting the shuffled dataset into a holdout set and a training set. The holdout set is taken from the beginning of the shuffled data up to the number of examples we previously decided to reserve for evaluation. The training set then consists of all remaining examples from that point to the end of the dataset. This approach uses every example exactly once and avoids any overlap between the two sets, preserving a clean and reliable split for training and evaluation. We start by collecting all unique identifiers from the original dataset to have a complete list of examples. Then we create one set containing the identifiers used in the training data and another set for the holdout data. By comparing these sets, we can confirm that each example appears in only one of them. This process ensures there is no overlap between the training and holdout sets. The code ensures that no example appears in both the training and holdout sets by checking for any overlap between their IDs. It finds the intersection of the two ID sets, and if any ID is shared, it raises a runtime error with a message that overlap has been detected. This safeguard is essential because it preserves the integrity of the data split and keeps the evaluation set truly independent from the training set. We verify that the number of training examples plus the number of holdout examples equals the size of the original dataset. This check ensures that no data has been lost or duplicated during the split. If the sizes do not add up correctly, the system raises a runtime error. This safeguard confirms that the dataset has been split properly and that all examples are accounted for. The code first prints the total number of examples in the full dataset to establish its overall size. It then prints how many examples are assigned to the training set after the holdout split, confirming that this portion has the expected size. Finally, it prints the number of examples in the holdout set to verify that this subset is also correctly sized. Together, these outputs provide a quick check that the dataset has been split as intended. We begin by printing a short message to indicate that we are about to display some sample training examples. Then we loop through the first 3 items in the training set, and for each one, we print its identifier, its text, and its label. This quick preview shows the structure and content of the training data and helps us confirm that the data split worked correctly and that everything is in the expected format. We begin by printing a short header to indicate that we are about to display all holdout examples, which is practical because the dataset is small. Then we loop through each example in the holdout set and print its identifier, the review text, and its label. Showing every holdout example like this makes it easy to inspect the data reserved for evaluation, confirm that the split is correct, and understand the structure of the dataset. This script shows how to create a simple holdout split using a small synthetic dataset of 20 labeled sentiment examples. It sets a random seed for reproducibility, builds examples with an ID, text, and positive or negative label, then shuffles the data and splits it into training and holdout sets using a holdout fraction of 25%. The holdout size is computed with a floor operation, so it does not exceed the intended proportion. The script checks that there is no overlap between the 2 sets and that their combined size matches the original dataset. Finally, it prints the total number of examples, the sizes of the training and holdout sets, and a few sample entries from each, illustrating how to prepare a separate evaluation set for machine learning tasks. Choosing split ratios. When splitting a small dataset into training, validation, and test sets, you must balance learning and evaluation. If you allocate too much data to training, the validation and test sets become too small, and performance estimates can be unreliable and heavily influenced by outliers. If you reserve too much for validation and testing, the model may not see enough examples to learn meaningful patterns. For instance, with only 500 labeled emails, using half for evaluation leaves too few for the model to learn the full diversity of the data. The key is to choose a split that provides enough data both to train the model well and to estimate its performance on new data with reasonable stability. When starting a machine learning project, a common approach is to use most of your data for training and a smaller portion for testing, often around an 80-20 split, with some of the training data reserved for validation if needed. For smaller datasets, these ratios may need to change, such as using more data for training when the data is very similar, or keeping more for validation and testing when the data is diverse. The key is to look not just at percentages, but at the actual number of examples in each split. Each subset must be large and varied enough to let the model learn useful patterns while still providing reliable evaluation results. When deciding how to split your dataset, focus on how you will validate and refine your model. If you plan to test many model variations or hyperparameters, your validation set must be large and representative enough to give reliable feedback, rather than being dominated by a few unusual cases. With very small datasets, a tiny validation set can easily mislead you, so you may need a larger validation portion or use cross-validation, while still keeping a separate test set for final evaluation. There is no single best split ratio, because the right choice depends on your dataset size and diversity, how complex the task is, and how often you expect to iterate on your models. Random versus ordered splits. When splitting a small dataset into training and validation sets, you can either assign examples randomly or keep their original order. A random split gives each example an equal chance to be in either set, which usually makes the sets similar and supports balanced performance. An ordered split is simpler, but can be risky if the sequence reflects patterns that will not appear when the model is actually used. The best choice depends on how the data will be encountered in real-world deployment. When your data has a meaningful order, such as time or production stages, the way you split it into training and validation sets matters a lot. Randomly shuffling time series data can mix past and future points, which does not match how the model will be used in practice. Instead, you should usually train on earlier data and validate on later data to better simulate predicting future values. The same idea applies in settings like manufacturing, where changes such as a new sensor may occur over time. Preserving the original order helps you evaluate whether a model trained on older data will still perform well on newer data and ensures the evaluation reflects real-world conditions. For small, non-sequential datasets, a random train and validation split is usually safer because the data often arrive in bursts that do not represent the full population. If you split by order, early records might come from one subgroup and later records from another, so poor validation results could reflect these differences rather than a bad model. The reverse can also happen if data quality improves over time, making the model look better than it really is. Randomly mixing entries helps both training and validation sets contain a similar mix of cases, so always consider what the order of your data represents and choose the split that best matches how the model will be used in practice. Splitting mistakes. Overusing test sets. Using the test set too often can distort how well you think your model performs. The test set should act like a final exam, used only once to measure performance on new data. If you repeatedly evaluate different model versions on the same test set, you end up tuning the model to the quirks of that specific data. This makes the reported performance look better than it really is, and weakens the test set as an unbiased benchmark for truly new data. A team builds a model to predict customer cancellations and keeps adjusting features and settings based on how well each version does on the test set. Over many iterations, they favor versions that happen to score well on this particular test data, even when that success is partly due to chance. As a result, they end up with a model that looks highly accurate on the test set, but performs poorly on new customers. This happens because they have unintentionally tuned their entire process to the test data, so it no longer serves as an unbiased benchmark of real-world performance. This problem appears not only in business, but also in areas like medical imaging and natural language processing, where data is scarce. Researchers may repeatedly test new methods on the same small dataset and gradually tune their models to those specific examples instead of to a wider variety of cases. As a result, the models can look very strong in reported results, but perform poorly on truly new data. By overusing the test set, it effectively becomes part of the training process, and the reported performance becomes overly optimistic. Peaking at evaluation. Peaking at evaluation happens when validation or test data influences how you adjust a model. Each time you tweak the model after checking its performance on this data, you are indirectly training on it. Over many such adjustments, the model becomes tuned to the quirks of the validation set, so its reported performance looks better than it really is. As a result, the model may seem strong on familiar evaluation data, but fail to generalize well to new, unseen inputs. Subtle overfitting occurs when a team repeatedly tweaks a model using the same validation data, such as in credit risk modeling, to squeeze out small gains in validation accuracy. Over time, the model starts to capture quirks specific to that validation set, so the validation results no longer reflect how it will perform on truly new data. In effect, the validation set becomes part of the training process, and when the model is deployed, its performance often drops. This problem also arises in areas like medical diagnosis, where models tuned to data from one hospital may not generalize well to other hospitals or patient populations. Repeatedly checking the same validation set and choosing the model with the highest score can quietly bias decisions about when to stop training or which algorithm to use. This kind of peaking risks treating random noise as meaningful patterns, which makes performance estimates look better than they really are. Those overly optimistic estimates can mislead stakeholders and cause resources to be invested in models that fail in real-world use. To reduce this risk, you should limit how often you change your approach based on validation results and treat validation data as a limited resource. Python code, peaking at evaluation. This script demonstrates how peaking at evaluation results can affect model performance. It uses a very small synthetic regression dataset to keep the example simple. By repeatedly reusing feedback from the validation set, the model is allowed to overfit to that specific data. The goal is to show how this practice can give an overly optimistic impression of how well the model will generalize. We begin by importing NumPy, a key Python library for numerical computing. NumPy allows us to work efficiently with arrays and perform fast mathematical operations. This capability is essential for the kinds of numerical tasks and data handling we will carry out in this script. We set a fixed random seed in NumPy so that any random numbers generated by the script are always the same each time the code runs. This makes the results reproducible, which is important for debugging and checking that our work is correct. By controlling the random seed, we can reliably repeat experiments and verify that changes in output are due to code changes, not random variation. We create 60 evenly spaced numbers between 0 and 1 and reshape them into a two-dimensional array with a single column to serve as input features. This simple setup lets us model a basic linear relationship in a controlled way. Using these structured inputs, we can focus on how a regression model is fitted and how its performance is evaluated. We create target values by defining a simple linear pattern and then adding a bit of randomness. For each input value, we multiply it by 2 and add 0.3 to form the basic linear trend. To make the data more realistic, we then add noise drawn from a normal distribution with mean 0 and a small standard deviation of 0.05. This process simulates real-world measurements that naturally include some variability around an underlying linear relationship. Before splitting the data, we first verify that the input and target arrays have the correct shapes. We check that the input array has 60 rows and 1 column, and that the target array contains 60 values. This assertion step confirms that the data is structured as expected and helps prevent shape-related errors in later processing. We begin by creating indices to split our dataset into training, validation, and test sets. Using a numerical range from 0 to 29, we select the first 30 samples to form the training set. Defining these indices explicitly ensures that the same data points are always used for training. This consistency is important for reproducible results and controlled experimentation. We select validation indices by choosing data points with positions from 30 to 45 in the dataset. These specific entries are set aside and not used for training. Instead, they serve as validation data so we can test how well the model performs on examples it has not seen during training. We define the test indices by selecting data points from 45 to 60, which gives us the last 15 entries in the dataset. These points are reserved for testing the model on data it has not seen during training. By keeping this test set separate from the training and validation sets, we can more accurately measure how well the model generalizes to new, unseen data. We form the training data by using the training indices to pick out specific input features and their corresponding target values. This selection splits the original dataset into a training subset. That subset is then used to fit or train the model. We build validation arrays by selecting specific input features and target values using the validation indices. These arrays form a separate validation set that the model does not see during training. Using this unseen data allows us to evaluate how well the model generalizes. It also helps prevent overfitting by providing an independent dataset for tuning model parameters. We build the test arrays by picking the elements from the original input and target arrays that match the test indices. This creates a separate test set that the model has not seen during training or validation. Keeping this test set independent is essential for fairly evaluating how well the model performs on truly unseen data. Mean squared error is a common way to measure how accurate predictions are. To use it, we first check that the true values and predicted values have the same shape, so the calculation is valid. After confirming this, we compute the average of the squared differences between each true value and its prediction. The result is a single number that represents the typical size of the prediction error and helps compare how well different models perform. This code computes the mean squared error by taking the difference between each true value and its predicted value, squaring those differences, and then averaging them. The averaging is done with a numerical library, so the result is a single floating point number. This value measures how closely the predictions match the actual data, where smaller mean squared error indicates better predictive performance. This function fits polynomial regression models by first building a Vandermonde matrix, which represents polynomial features of the input data. Each column of this matrix is a power of the input values starting from power 0 up to the chosen degree. By transforming the data in this way, the model can capture polynomial relationships and fit curved patterns instead of being limited to straight lines. This code solves a least squares problem to find the coefficients of a polynomial that best fit the data. It uses a numerical linear algebra routine from a scientific computing library, which takes a Vandermonde matrix of polynomial terms along with the target values. The routine returns the polynomial coefficients that minimize the sum of squared differences between the predicted and actual values. Any extra outputs from the function are ignored, which is why they are assigned to a placeholder that is not used. This function outputs the coefficients learned when fitting the polynomial model. These values represent the model's parameters and capture what it has learned from the training data. By returning these coefficients, the model can later be reused to evaluate or predict new data points without needing to be refit. This function predicts values from a polynomial by first building a Vandermonde matrix from the input data. Each column of this matrix represents the input values raised to increasing powers, starting from power 0 up to the polynomial's degree. The number of columns is chosen to match the number of polynomial coefficients. Once this matrix is built, the function multiplies it by the coefficient vector to efficiently compute the polynomial predictions. This step generates predictions by multiplying the matrix of polynomial features, called the Vandermonde matrix, with the learned polynomial coefficients. The result of this matrix multiplication is a set of predicted values. These values represent the model's output for the given input data based on the fitted polynomial relationship. The code sets up a list of polynomial degrees from 1 to 12 to test different levels of model complexity. By looping over these degrees, it fits multiple polynomial models to the same data. Comparing their performance helps reveal which degree provides a good fit to the training data, while still generalizing well to new, unseen data. This process helps select an appropriate model complexity. We begin by creating a list to store validation errors, specifically the mean squared error for each polynomial degree we test. As we evaluate models with different degrees, we record their error values in this list. Later, we use these stored errors to compare the models and identify which polynomial degree gives the best fit to the validation data. We create an empty list to store the test error for each polynomial degree we try. By recording these errors, we can later compare how well models of different complexity perform on unseen data. This comparison helps us understand how increasing the degree of the polynomial affects the model's ability to generalize beyond the training set. We loop over a range of possible polynomial degrees, and for each one, fit a polynomial regression model to the training data. This means we compute the coefficients that best match the data for that specific degree. By repeating this process for different degrees, we can see how model complexity changes performance. This setup mimics how we might repeatedly check validation results to choose the most appropriate polynomial degree for the final model. We now use the current polynomial model to make predictions on the validation data. To do this, we apply the previously learned polynomial coefficients to the validation input features to produce predicted outputs. Comparing these predictions to the true values shows how well the model generalizes to new, unseen data. This step is essential for evaluating the model's overall performance. Now, we use the current polynomial model to make predictions on the test data. We take the test inputs and plug them into the polynomial using the coefficients we previously estimated. This produces predicted output values for each test example. These predictions will later be compared with the true test outputs to see how well the model generalizes to new, unseen data. We calculate the mean squared error on the validation set by comparing the true target values with the model's predictions and averaging the squared differences between them. This gives us a single number that summarizes how far, on average, the predictions are from the actual values. It is an important metric for judging how accurately the model performs on unseen data and for choosing between different models. We compute the mean squared error on the test data by comparing the true test values with the model's predictions. This measure tells us how well the model generalizes to new unseen data. We then store this error so we can later compare performance across different polynomial degrees and evaluate which model works best. The code saves each calculated validation mean squared error in a list called val errors, which records the validation performance for every polynomial degree tested. By keeping track of these errors, the script can later compare how well different polynomial degrees perform on the validation set. This comparison helps identify which degree gives the best validation performance. In turn, this allows the user to select the polynomial model with the most appropriate level of complexity. The code saves each test mean squared error in a list of test errors, with one entry for every polynomial degree tested. This list records how the model performs on unseen data for each level of complexity. By storing these values, the code can later compare how well different polynomial models generalize and identify which degree gives the best test performance. The code turns the list of validation errors into a NumPy array so the data is easier to index and manipulate. This makes it more convenient to work with the errors as a whole. As a result, it becomes simpler to analyze the errors and compare model performance across different polynomial degrees. The code turns the list of test errors into a NumPy array so the data is easier to work with. This conversion makes indexing the errors more convenient and supports efficient manipulation. As a result, it becomes simpler to analyze and compare the test error values in later steps. To choose the polynomial degree with the best validation performance, we apply a function that finds the position of the smallest value in the array of validation errors. This position, or index, tells us which degree gives the lowest validation error after peeking at the results. We then convert this index to an integer so it is in the proper format for later use. The code chooses the best polynomial degree by finding which option gives the lowest validation error. It uses the position of this minimum error to look up the corresponding degree from the list of candidates. This selected degree represents the model complexity that performed best during validation. Identifying it is important for comparing validation and test performance and for understanding how model complexity relates to overfitting. We take the validation error that corresponds to the model degree with the smallest validation error, using the index of the best degree found earlier. Then we convert this selected error value to a standard floating point number. This ensures the error is in a consistent numerical format, making it easier to use in later calculations or comparisons. We start polynomial regression with a degree of 1 as a simple baseline model. This baseline acts as a reference to judge how well more complex, higher degree polynomials perform. By comparing their results to this basic model, we can see whether increasing the polynomial degree actually improves performance and by how much. We first need to locate the baseline degree within the list of candidate degrees. To do this, we use a list operation that returns the position or index of the baseline degree. This index tells us where the baseline model sits among all candidates. We then use that position to look up the corresponding validation and test errors for the baseline model later in the script. The code takes the validation error at the baseline index and converts it into a floating point number. This creates a clear numerical value that represents the baseline model's error. Having this value in a consistent numeric format is essential for accurately comparing the baseline model's performance with other models and for any further analysis. We obtain the baseline test error by taking the test error value at the baseline index and converting it into a floating point number. This step standardizes the value so it can be handled consistently in our analysis. With the error in this format, we can easily compare it to other error metrics later on. We select the test error that corresponds to the model degree with the lowest validation error. To do this, we find the position of the smallest validation error and use that position to look up the matching test error in the test errors array. We then convert this selected test error to a floating point value so it is consistent and ready for later calculations and comparisons. The code begins by printing a short message that introduces an experiment about model selection. It explains that the experiment will simulate what happens when we peek at validation data to choose how complex a model should be. This introduction sets the stage for the results that follow and emphasizes that using validation data in this way can lead to problems. Overall, it prepares the listener to understand the potential pitfalls of relying on validation performance to guide model complexity. We display a message showing the degree of the baseline model and its validation mean squared error. This tells us how well the simplest possible model fits the validation data. By knowing this baseline performance, we have a clear reference point for judging whether more complex models actually provide an improvement. The code reports the baseline model's polynomial degree and its test mean squared error. It uses the chosen baseline degree to indicate how complex the model is and looks up the corresponding test error that was computed earlier. The error value is rounded to 4 decimal places before being shown. This output is used to compare how well the baseline model performs relative to more complex models. We report the degree of the polynomial model that was selected based on validation performance during training. This degree is chosen because it produced the lowest validation mean squared error among all candidate models. We also state this validation error rounded to 4 decimal places to summarize how well the chosen model fits the validation data. We report the test mean squared error for the model degree chosen after looking at validation errors. This shows that picking model complexity based on validation performance can be overly optimistic. The model may appear to perform well during validation, but fail to generalize to new, unseen data. The code prints a message emphasizing a key result from the experiment. Although the validation error looks best for the chosen polynomial degree, the test error is actually higher. This mismatch suggests that the model is overfitting to the validation data. In other words, the validation performance is overly optimistic and does not generalize well to new, unseen data. This script shows what happens when you repeatedly peek at validation data to choose model complexity. It creates a simple regression problem, splits it into training, validation, and test sets, and fits polynomial models of different degrees. The degree with the lowest validation mean square error is selected, mimicking the common practice of using validation performance to guide model choice. The result is that this chosen model often overfits and performs worse on the test set than a simpler baseline. This demonstrates that validation error can be overly optimistic and that test data is needed for an unbiased evaluation of model performance. Common leakage scenarios. If you split data incorrectly when building a model, you can accidentally cause data leakage, which makes performance look better than it really is. This often happens when the same entity, such as a customer in a loan default model, appears in both the training and test sets. The model then learns from part of that customer's history during training and is tested on other records from the same customer. Because the test data is not truly new, the model gets an unfair advantage and appears more accurate than it would be on completely unseen customers, giving a misleading picture of its real-world performance. Applying pre-processing steps like normalization, feature scaling, or feature selection to the entire dataset before splitting can cause data leakage. For example, if you standardize a medical dataset using statistics from all patients, the training and test sets influence each other, so the model is indirectly tuned to the test distribution. Likewise, choosing features based on their correlation with the target using the full dataset lets the model effectively see the test labels. As a result, evaluation metrics become overly optimistic and no longer provide a trustworthy estimate of true test performance. Data leakage happens when a model uses information that would not be available at the time of prediction, which leads to overly optimistic results. This can occur in time series forecasting if future data, such as rolling averages that cross the train and test split, are used. In hospital models, it can happen when post-discharge information, like final diagnosis codes, is included, even though the model should only use data available at admission. In credit scoring, using a feature that reveals whether a customer eventually defaulted also creates leakage. To avoid misleading performance, make sure data splitting and pre-processing only rely on information that would be known at the actual prediction time. Python code. Common leakage scenarios. This script demonstrates simple examples of data leakage and shows why correct dataset splitting is so important. It contrasts proper splitting methods with incorrect ones that accidentally let information from the test set influence training. By comparing these approaches, you can see how leakage makes model performance look better than it really is. The main goal is to help you recognize and avoid leakage, so your evaluation results remain trustworthy. The code starts by importing two built-in Python modules, random and statistics. The random module is used to create random numbers, and by setting a fixed seed, it makes these random operations reproducible, which is important for debugging and testing. The statistics module provides tools for basic statistical calculations, such as computing the mean, which will later help define thresholds for a simple rule-based model. Together, these imports prepare the environment for the upcoming steps of generating data and analyzing it statistically. We begin by setting a fixed random seed using the random module so that any random operations in our script always produce the same results. This makes our work reproducible, meaning we can run the code multiple times and get an identical sequence of random numbers. It is especially important when debugging or sharing code because it allows others to replicate our results exactly. In short, a deterministic random seed provides consistency and reliability in programs that use randomness. We create a small, synthetic customer dataset where each customer has an ID, an income, a debt level, and a default status. The ID runs from 1 to 12, and income increases in a simple linear way with the ID, starting at 30,000. Debt is also generated by a simple rule that depends on the remainder when the ID is divided by 3. The default status is set to 1 when the ID is divisible by 4, and 0 otherwise. This design produces a predictable pattern that is useful for testing and demonstration. The code verifies that the customer list contains exactly 12 entries. This check keeps the example dataset small and manageable. It also confirms that the data generation step worked correctly. If the list does not have 12 items, the program raises an error to indicate a problem with creating the dataset. This section describes a function that measures prediction accuracy. It counts how many predicted values match the true values, then divides this count by the total number of true values to get an accuracy score. If there are no true values, it returns 0 to avoid dividing by 0. Overall, it provides a simple way to see how closely predictions match actual outcomes. The accuracy function measures how well predictions match the true values. It counts how many predicted values are exactly the same as the corresponding true values, then divides this count by the total number of true values to get an accuracy score. If there are no true values to compare, it returns 0 to avoid dividing by 0. This provides a simple way to evaluate prediction performance. This line computes prediction accuracy by taking the number of correct predictions and dividing it by the total number of true values. It includes a check for the case where there are no true values. If the list is empty, it returns 0 instead of attempting the division. This prevents division by 0 errors and makes the function more robust in edge cases. To build a simple rule-based model from the training data, we first separate customer incomes into 2 groups, those who defaulted and those who did not. If one of these groups is empty, meaning there are either no defaults or everyone defaulted, we set the decision threshold as the average income across all customers. Otherwise, we compute the threshold as the average of the mean incomes of the 2 groups. We then use this income threshold to predict whether a new customer is likely to default. The function first builds a list of incomes for training examples where the customer defaulted, meaning the default value is 1. It then builds a second list of incomes for training examples where the customer did not default, with a default value of 0. These 2 income lists are later used to help choose an income threshold that can be used to predict whether a customer is likely to default. The code first checks whether the income list for customers who defaulted or the list for those who did not is empty, because without both groups, it cannot compute a meaningful separating threshold. If either list is empty, it falls back to using the average income across all training data as the threshold. If both groups have data, it instead sets the threshold to the average of the mean incomes of the 2 groups. This creates a middle value intended to separate customers likely to default from those who are not. This function returns the previously calculated threshold value, which is the income level used to separate customers who are likely to default from those who are not. By returning this value, other parts of the program can use it to make predictions on new customer data. This keeps the decision rule in one place and ensures the model's decision boundary is applied consistently across different datasets. This part of the code uses a previously learned income threshold to make predictions. It defines a function that takes several data rows and a threshold value, then checks each customer's income. If the income is greater than or equal to the threshold, it predicts a default of 1. Otherwise, it predicts 0. In this way, it applies a simple rule based on income to classify customers and evaluate how well this rule works on the dataset. This function classifies each row in a dataset using a simple income rule. It compares the income in a row to a given threshold value. If the income is greater than or equal to the threshold, it predicts a default by returning 1. If the income is below the threshold, it predicts no default by returning 0. In this way, every row is labeled based solely on how its income compares to the threshold. This step builds a list of predictions by going through each row of the input data and comparing the customer's income to a chosen threshold. If the income is greater than or equal to that threshold, the model predicts a value of 1, meaning the customer is classified as a default. If the income is below the threshold, it predicts a value of 0, meaning no default. In this way, a simple rule based on income alone is used to classify each customer. We create 2 empty lists to hold customer records, one for training data and one for testing data. As we loop through each customer in the dataset, we copy their information into a new dictionary. The original record goes into the training list, and the duplicate goes into the testing list. This means the same customers appear in both sets, creating a leaky split that can make the model's performance look better than it really is. We train a simple rule-based model using the leaky training data by calling a function that computes an income threshold. This function looks at the incomes of customers who defaulted and those who did not, and tries to find a value that separates these two groups. If it cannot find a clear separation, it uses the average income as the threshold. Later, this threshold is used to predict whether a customer will default based only on their income level. The code uses the learned threshold to predict which customers in the leaky test data will default based on their income, then collects the true default outcomes for those same customers. It compares the predicted defaults to the actual outcomes to compute accuracy. This accuracy score shows how well the model appears to perform when the test data is not properly separated from the training data. Because of this data leakage, the measured performance is often unrealistically high and does not reflect how the model would behave on truly unseen data. To avoid data leakage, we split the customer dataset into separate training and test sets. The first 8 customers are used for training, so the model learns from those specific examples. The remaining customers, from the 9th to the 12th, are reserved for testing. This way, the test set contains entirely new customer identities that the model has not seen before, allowing for a more realistic evaluation of its performance. The code makes sure that no customer appears in both the training and test datasets by comparing their customer ID sets. It first collects all customer IDs from the training data and all IDs from the test data, then checks whether these two sets share any elements. If the intersection is empty, the assertion succeeds, confirming that the datasets do not overlap. This separation is essential to prevent data leakage and to ensure the model is evaluated only on customers it has not seen during training. We train the model using only the designated training data by calling a function that builds a simple rule-based model from this split. The function computes an income threshold that separates customers who defaulted from those who did not. And this threshold will later be used to make predictions on new, unseen data. By restricting training to the proper training set and excluding any information from the test set, we avoid data leakage and can more accurately evaluate the model's true performance. We use the learned threshold to make predictions on the test dataset by applying it to each customer's income to decide whether they are predicted to default. We then take the actual default outcomes from the test data and compare them with these predictions. From this comparison, we compute the accuracy, which tells us how well the model performs on data it has never seen before. The code first reports the model's accuracy using a leaky data split and notes that the result looks unrealistically high, which is a common warning sign of data leakage. It then shows the accuracy from a proper data split, which appears more realistic. This contrast demonstrates that the same modeling approach can seem very reliable or not, depending on how the data is split. The explanation emphasizes that leakage happens when information from the test data influences training, artificially boosting performance. To avoid this, it recommends designing data splits that closely match how the model will be used in real-world deployment. This script shows how data leakage can distort model evaluation by comparing two ways of splitting a dataset. It uses a small synthetic customer dataset with income, debt, and default status, and first creates a leaky split where the same customers appear in both training and test sets. This leads to unrealistically high accuracy because the model is effectively tested on data it has already seen. It then performs a proper split with no overlap between training and test customers, producing a more realistic accuracy. The main lesson is that data splits must mimic real-world deployment and avoid any overlap to prevent leakage and misleading performance results. In this lecture, you learned to describe the roles of training, validation, and test splits in model development, propose simple ways to split a small dataset into separate parts, and explain how improper splitting can lead to overly optimistic performance estimates. In the next lecture, Lecture B, we will go over cleaning and scaling. Thank you for your attention. See you all in the next lecture.